In the previous video, we briefly learned about the principles and structure of a nuclear power plant. Let's take another look at the structure of a nuclear power plant. Inside a reactor building, there is a reactor in the center, 4 pumps, 2 steam generators, and 1 pressurizer. Reactor coolant passes through the fuel rods inside the reactor, gradually becoming hotter. The heated reactor coolant moves through pipes to the steam generators. Inside the steam generators, the reactor coolant flows through U-shaped pipes, heating the feed water outside the pipes. The feed water outside the pipes turns into steam and travels through the pipes. The steam first rotates the high-pressure turbine. After rotating the high-pressure turbine, the steam loses energy and the temperature goes down. So it is then passed through a moisture separator reheater, which raises its temperature again and then goes on to rotate the low-pressure turbine. After rotating the low-pressure turbine, the steam is cooled down to water with the help of seawater. Condensed water is then sent back to the steam generator using pumps. In this video, we will explore the structure and equipment of a power plant in more detail. First, we have a nuclear reactor. A reactor is made of carbon steel alloy and has a height of 14.6 meters and a diameter of 4.5 meters. It contains nuclear fuel at the bottom and control rods at the top to control the neutrons. There are also interconnected pipes for the water to flow. Below the reactor is where the nuclear fuel is placed. Uranium is sealed within ceramic pellets to create fuel pellets. These pellets are then stacked together, filled with helium gas, and finally enclosed within fuel rods. Several fuel rods are bundled together to form fuel assemblies, and many such assemblies are placed in a reactor. At the top, there are control rods. Control rods are devices that absorb neutrons. Uranium undergoes fission when it collides with neutrons. If there are more neutrons, more uranium will undergo fission, and if there are fewer neutrons, only a small amount of uranium will undergo fission. There are holes in between the nuclear fuel where the control rods are inserted. When the control rods are inserted deeply into the nuclear fuel, they absorb more neutrons, reducing nuclear fission. As the control rods are raised, more neutrons are available, leading to increased number of nuclear fissions. Several control rods are attached to a driving mechanism, which is electromagnetically operated to move up and down. In case of a power outage causing an accident, the driving mechanism would fall freely. This would result in all the control rods being inserted between the nuclear fuel, absorbing most of the neutrons and preventing nuclear fission. Reactor coolant inside the reactor is circulated using a reactor coolant pump. Reactor coolant has a pressure of about 150 times that of atmospheric pressure. Water tends to flow backward through the narrow gaps between machineries. To prevent this, higher pressure water is sprayed into the upward flow, preventing any water from flowing in a reverse direction. 4 pumps are powerful enough to fill an Olympic-sized swimming pool in just 1 minute. Reactor coolant sent to the reactor through the pumps hits the walls and then moves downward. As it passes through the fuel rods, it moves upward, absorbing heat and becoming hotter. The heated reactor coolant is then sent to the steam generator. Reactor coolant flowing through the reactor serves not only to transfer heat, but also to slow down the speed of neutrons, acting as a moderator. Neutrons need to flow slowly for an efficient nuclear fission. When neutrons collide with water, their speed is reduced. In nuclear power plants that use 4 to 5% enriched uranium, water called light water is used as a moderator. Hydrogen is an element composed of 1 proton and 1 electron. Among isotopes, there are hydrogen-2, deuterium, and hydrogen-3, tritium. Deuterium consists of 1 proton and 1 neutron, while tritium consists of 1 proton and 2 neutrons. Water made from a hydrogen atom with 1 proton and 1 electron is called light water, while water made from a deuterium atom is called heavy water. Ordinary water mostly contains light water with a small amount of heavy water. Some nuclear power plants use natural uranium without enrichment, where heavy water is used as a moderator. Natural uranium has a low concentration of uranium-235 of about 0.7%, and so the speed of neutrons needs to be reduced further. This is because slower neutrons lead to more series of nuclear fission. Heavy water slows down the speed of neutrons more than light water simply because it is heavier. Therefore, nuclear power plants using natural uranium use heavy water as a moderator. Both heavy water and light water-based nuclear power plants have their advantages and disadvantages, but a majority of nuclear power plants use light water-based reactors. Water heated in the reactor enters the steam generator, and there is a pressurizer in between. A pressurizer is a device that increases the pressure of the water, preventing it from boiling even at high temperatures. A pressurizer contains water up to about half its height, and above that there is steam. By using heaters below, the temperature goes up and the water starts to boil. When water boils, steam is generated, and the pressure from this steam compresses the water, increasing its pressure. If the pressure becomes too high, the spray system above releases cooler water to reduce the pressure. Under normal conditions, the spray system works in tandem to regulate the pressure. Reactor coolant, heated in a reactor, moves through the pipes to the steam generator. Hot reactor coolant flows through approximately 13,000 U-shaped tubes within the steam generator, making a full circuit. As 320-degree hot reactor coolant moves through the pipes, it heats feed water outside the pipes. The heated reactor coolant in the pipes cools down after transferring the heat energy to the outside feed water and leaves from the rear pipes. The reactor coolant is then sent back to the reactor through the pipes. After turning the turbine, the condensed feed water re-enters the steam generator through a sideline and moves downward. The descending feed water passes through the space between the pipes, acquiring heat from the hot reactor coolant flowing in the pipes, and gets transformed into steam. Steam contains some liquid particles which have not yet reached the gaseous state. These liquid state steam particles are called moisture. When the steam in this state enters the turbine, it can cause damage to the turbine blades. To prevent this, there is a device above the steam generator that separates moisture from the steam. Inside a yellow cylinder, there is a device shaped like a windmill that causes the moisture to condense back into water. Steam, with most of the moisture removed, then goes through another separation process in the grid-type separator, resulting in steam that is almost 99% gaseous. Steam produced in the steam generator travels through pipes and enters the turbine. Incoming steam first rotates the high-pressure turbine. Inside the turbine, there are many blades. When steam collides with these blades, the turbine starts to rotate. Steam used in the high-pressure turbine exits through holes on both sides, losing its energy. Steam that exits is not wasted. It is used to rotate 3 low-pressure turbines. However, as this steam loses energy, its temperature decreases and some of it becomes moisture. Steam, which contains moisture after passing through the high-pressure turbine, is sent to the moisture separator reheater. Inside this equipment, there are heaters. Some of the steam entering the high-pressure turbine is diverted to these heaters, and the steam that lost energy is heated once again. Moisture that did not turn into steam falls downward and becomes water, which is then reused. Steam passing through the moisture separator reheater then rotates 3 low-pressure turbines. Steam, having lost a significant amount of energy after rotating the low-pressure turbine, is sent to the condenser located below. In the condenser pipes, cold seawater flows, causing the steam to lose heat and condense back into water. The area between the turbine and the condenser experiences a significant temperature difference, and the steam, being voluminous, transforms into water. This creates a nearly vacuum-like condition within the condenser. As a result, the steam used in the turbine quickly moves to the condenser. Fluids flow from areas with high pressure to areas with low pressure. Steam, being at high temperature and pressure in the turbine, develops a force to move toward the low temperature, low pressure condenser. This force results in higher speed of movement and, in turn, increases the force that rotates the generator. Therefore, the greater the temperature difference between 2 points, the more efficiently the energy can be utilized. Water stored in the condenser is sent back to the steam generator to be used again. The water is relatively cold, around 30 to 40 degrees, while the temperature at which it turns into steam in the steam generator is about 320 degrees, resulting in a significant temperature difference. Similar to how adding hot water to boiling water can cause it to boil quickly again, while adding cold water will make it harder to boil, Sending cold water from the condenser directly to the steam generator will not easily turn it to steam. To address this issue, the water is passed through a preheater before being sent to the steam generator, raising its temperature to around 235 degrees. Inside the preheater, there are pipes through which hot steam flows, and the hot water passes through these pipes, gradually increasing the temperature of the water. As the water's temperature does not rise instantly, it goes through 7 stages to gradually raise the temperature. Water, now at an increased temperature, is sent to the steam generator to be transformed into steam. Till now, we have examined the equipment used in power generation. Now let's take a look at the structure of the building that houses and operates the power plant. Firstly, the containment building that houses the reactor is constructed in a dome shape, with a diameter of 45 meters and a height of 75 meters. Above the building there are cranes. Cranes are used during the initial construction of the power plant to transport equipment, and during regular operations they are used to examine the equipment or open the reactor lid for replacing nuclear fuels. Additionally, there is a spray above the crane, used to spray water in case of accidents to cool down the reactor. The interior of the dome is mostly empty. The dome shape is designed to evenly distribute pressure. In the event of an accident inside the building must withstand the pressure without releasing any contaminated substances outside. By creating a dome shape, the volume increases, allowing more gas to be confined and pressure to be evenly dispersed. One of the concerns we have is whether a nuclear power plant could explode like a nuclear bomb. However, the uranium used in nuclear bombs is enriched to over 90%, while the uranium used in power plants is enriched to only 4 to 5%, so it will not explode. To illustrate, when you light alcohol with a concentration of over 90%, it catches fire. But if you try to light beer with an alcohol concentration of 4%, it does not catch fire. Similarly, the uranium used in power plants does not explode. The worst-case scenario that can occur inside the reactor building is the generation of steam or hydrogen gas due to the meltdown of the reactor. Fukushima Power Plant also experienced explosions due to hydrogen gas. To withstand the pressure caused by newly generated gas, the ceiling was constructed in a dome shape. To remove hydrogen gas, there are devices installed using electricity to generate sparks and remove hydrogen, as well as devices that automatically remove hydrogen by chemical reactions during power outages. When we think of nuclear accidents, Chernobyl and Fukushima come to mind. Both were not dome-shaped but had a shape of a square, which made them weaker against pressure. The dome shape is more costly to construct, but it is chosen for safety reasons. The inner walls of the reactor building are made of reinforced concrete with a thickness of 1.2 meters. Steel reinforcements about the size of a human palm are densely placed in the concrete. Additionally, thick steel reinforcements, commonly used in bridge construction, surround the building from all sides, helping it withstand pressure. In a nuclear power plant, there are 5 layers of radiation protection. The first barrier is the fuel pellet surrounding the uranium. The second barrier is the fuel rod enclosing the pellet. The third barrier is the reactor vessel that shields radiation. And the fourth barrier is the steel plates coating the reactor building, providing radiation protection. Finally, the outer wall of the building acts as the 5th barrier, preventing radiation leaks. Auxiliary buildings surrounding the reactor containment building serve the purpose of preventing the release of internal radioactive materials in the event of an accident. These buildings are independently arranged, allowing for compartmentalization to prevent the spread of damage in case of accidents. They also house various safety devices in separate areas for handling radioactive materials. The fuel storage building is where new and used nuclear fuel are stored. It is filled with borated water, which inhibits nuclear fission reactions, and the fuel is cooled here for at least 5 years. In the event of a power outage due to an accident, emergency diesel generators provide backup power. The emergency power facilities are all located above ground and are covered with waterproof barriers as a precautionary measure. The main control room is the space where the power plant is managed. It controls the power plant based on a distributed control system displayed on large information boards. The nuclear power plant has 2 reactor buildings. Constructing 2 buildings is more economically advantageous since shared spaces can be utilized in a cost-effective manner. Nuclear power plants are built on bedrock rather than soil, since bedrock is much stronger against earthquakes, which helps reduce the impact of seismic events. Therefore, Nuclear power plants are specifically designed to be constructed on bedrock terrains. The bedrock is excavated and a concrete foundation is built before placing the reactor on top. A nuclear power plant is designed to shut down in the event of a magnitude 6.5 or higher earthquake. The latest APR 1400 reactors can withstand earthquakes up to magnitude 7. It doesn't mean they collapse at magnitude 7. They are engineered to continue functioning with no equipment failures, ensuring a safe shutdown. All equipment is installed with safety devices capable of withstanding earthquakes. Additionally, in case of tube breakage or any issues, all valves are configured to automatically close, causing the power plant to stop. If the plant doesn't stop during an accident, it could lead to a more significant disaster. A plant's automatic shutdown function is an effective accident prevention measure. Radiation exists around us at all times, but in amounts small enough not to pose health risks. The interior of the power plant buildings is similar to our living spaces, and even inside the reactor building there is no significant amount of radiation. However, when working inside the reactor building, wearing safety equipment is required. Waste generated in a nuclear power plant consists of both high-level radioactive waste, HLW, and low-level radioactive waste, LLW. HLW mostly includes used nuclear fuel, while LLW refers to waste with relatively lower levels of radioactivity, such as work clothing or tools used by plant workers. LLW is contaminated with relatively low levels of radiation compared to HLW. Even though the radiation levels are low, LLW is stored and managed in disposal facilities located deep in underground caves, tens of meters below the surface. At South Korean light water nuclear power plants, high-level radioactive waste, which is the used nuclear fuel, is stored and cooled in a wet storage facility filled with borated water for more than 5 years. Afterward, it is transferred to a dry storage facility on the nuclear power plant site, where it is placed in storage containers designed to shield the radiation. However, this dry storage cannot be a permanent solution. Used nuclear fuel needs to be permanently disposed of, ideally deep underground, hundreds of meters below the surface, isolated from our living environment. However, South Korea currently lacks a permanent disposal facility, and there are no interim storage facilities available either. Consequently, the used nuclear fuel is stored on the nuclear power plant sites until adequate facilities are furnished. To establish a permanent disposal facility, it will require more time as it necessitates national consensus. Nuclear power always carries with it risks even when managed with utmost care. Hence, this is why there is much ongoing research for safe usage of nuclear power and alternative energy development. One promising development in this regard is the Small Modular Reactor, SMR, which is being developed as a next-generation nuclear technology. SMRs bring together all essential components into a single containment vessel, including the reactor, steam generator, pressurizer, and pumps. Many developed companies are working on SMR development as a next-generation nuclear technology, and in 2012, South Korea became the first country to develop an SMR called SMART. SMR is relatively compact, standing about 35 meters tall with a diameter of around 9 meters, making it much smaller than the conventional containment building of large-scale nuclear power plants. It includes the reactor and control rods below with pressurizer above, and on the side there is a steam generator. On top of the steam generator there is a pump that continuously circulates water. Water passing through the reactor receives heat and becomes hot. This hot water is sent to the steam generator using a pump, where the water passing through the pipes gains heat and becomes steam. This steam then rotates the turbine to produce electricity. SMR has the advantage of being small in output but safe. Compared to large-scale nuclear power plants, it has a smaller heat output and applies revolutionary safety designs, allowing it to safely cool down the reactor even in emergency situations without electricity supply. Moreover, there are no connecting pipes in SMR. Pipes need to be connected through welding, and with the high temperature and high pressure water passing through the pipes at 320 degrees, even a minor welding defect could lead to accidents. As SMR doesn't involve a single pipe, it ensures greater safety. Additionally, SMR is manufactured in a factory and then installed at the power plant. As most major devices are manufactured in a factory, the quality improves, and the construction period can be shortened. Large-scale nuclear power plant APR 1400 produces 1,400 megawatts of electricity. In SMR, one unit has an output of 170 megawatts, and multiple units can be installed in one nuclear building. One unit can be used to produce electricity, while another unit can be used to produce hydrogen, ensuring flexibility in terms of its use. Due to its small size, SMR is less influenced by the location, allowing it to be installed near industrial complexes or cities close to the demand sites. Large-scale nuclear power plants take around 5 years from construction to electricity production. However, with SMR, the first module could start its electricity production from about 2 years after the start of the construction. Due to its many advantages in safety, flexibility, and efficiency, the demand for SMR is expected to increase over time. Nuclear energy is a knowledge-based energy source. Power plants that use fossil fuels spend a significant portion of their operating costs on importing fuel, resulting in a substantial amount of money flowing out of the country. In contrast, nuclear power plants only allocate 5% of their operating costs for importing fuel, while the remaining 95% stays within the country. Additionally, nuclear power plants do not emit carbon dioxide. 1 gram of uranium can replace 3 tons of coal. I hope this video has provided some help in understanding nuclear power generation. Thank you for watching.